G'day there, Glenn Morris from the Smart Energy Lab. Gee, it's brass monkey weather today. That's why I've got all my thermals on and my puff jacket, my beanie, totally puffed up. Anyway, today we're here to talk about AC and DC coupling. What is it, why would you use it, and what's the difference? So just to show you, before we get into the detail with some diagrams, what it looks like in the flesh. So behind me, I've got some Victron Multiplus 2s in a 3-phase configuration. Those are battery inverters. That means they can create AC power from a battery, and the batteries here are the Redflow Z cells. They're a zinc bromine battery, by the way, very interesting technology. We also have over here, AC coupled to this system, a Fronius Simo Gen 24 hybrid inverter. Now it does have its own battery, the BYD HVM battery beneath here, but it also can send surplus power across an AC bus, i.e. a switchboard, to the Victron system and charge the BYD batteries, the Redflow batteries, sorry. On top of that, we've also got DC coupling happening. Behind me is a MPPT. This is a maximum power point tracking charge controller, which has its own dedicated PV array connected to it, and it's directly charging the Redflow batteries. DC coupling is the simplest way of charging a battery. There's no inverters involved. It's DC-DC, and it's very high efficiency. So why would you have both? Well, we're going to explore that in the detailed diagrams following, but in a nutshell, it's about reliability. A system that has DC coupling is essentially more simple, doesn't require an inverter to be turned on to charge or to pass charge between an AC solar inverter and an AC battery inverter. It just directly charges a battery system. But then again, AC coupling is great for scaling to larger systems. So we've got both here in a really an off-grid system with high reliability in mind. Let's get into it. Let's take a closer look at how PV solar panel systems and battery systems are configured. There are many terms that are thrown around, such as AC coupling and DC coupling, but what I want to explain here is subtle differences and the major differences between different configurations of the two, and also an off-grid application as well. Now, this is a sort of an example of a very typical in a single line diagram format AC coupled system. So let's take a look at how it works. Now, this system here, essentially they had an existing solar inverter and PV array. So let's call this a retrofit system. They wanted to add battery storage to it. And in order to do that, you need a battery inverter and a battery. So we've got a battery inverter and a battery. Now, those sometimes are combined as a single product. So people will refer to a product as a battery, but it may well have an inbuilt inverter, and therefore its only interface with the switchboard is AC. There is no DC connections. Or there may be a separate battery inverter and a separate battery system. Now, the problem with this configuration as I've drawn it is that the battery inverter doesn't really know anything about what's going on unless there is an upstream energy meter. Now, this is not the DNSP's meter. This is a meter that will be supplied typically with the battery inverter and provide a communication system, usually wired, that will show the energy flow between the grid and the installation. Once that's visible to the battery system, it can then make decisions about what to do. For instance, let's say it's a sunny day and we've got 5 kilowatts of solar energy flowing to the main switchboard. The loads are relatively light, so we've got, let's say, 1 kilowatt of loads at the moment, 1 kilowatts, and the surplus 5 kilowatts would notionally, 4 kilowatts would notionally flow out to the grid. Now, because of the low value of exported energy, people really want to store that in a battery and use it at nighttime. So that meter, this meter here, sees that export of 4 kilowatts, communicates that with the battery inverter system, and the battery system starts to try and charge its battery at a rate close to or exactly what was being exported. So it may take a few moments to ramp that down, but what will happen is it'll divert as much of that energy as possible, in this case 4 kilowatts, into the battery system. So now it's charging the battery with surplus solar that the loads don't require. What about the reverse? How does a battery system support the loads? Well, let's wipe those out and start again. Let's say the customer is importing energy. So they're importing 2 kilowatts, and that 2 kilowatts is going to the loads. And it's nighttime, so there's no solar. Once again, the battery inverter will actually see this imported energy, and through that communication system with the battery inverter, it will see an opportunity to displace that imported grid power. So, and it usually happens over a period of like 30 seconds or so. It'll ramp towards a target of exporting 2 kilowatts. So it will try to export 2 kilowatts to support the loads. So there's the 2 kilowatts on the load, and we're got 2 kilowatts coming out of the battery system. And that's all because that meter allows the visibility of exchange of energy with the grid. So that's an AC coupled system. Let's look at some of the pros and cons of an AC coupled system. Now, essentially, it is a system that can be added to an existing installation. So there's no actual requirement that you buy the battery inverter and the solar inverter from the same vendor. They can actually be completely separate products, and therefore they don't have to be a proprietary solution. Adding it to an existing Grid Connect system is very easy. Just another main switch, which will be labeled battery inverter system. So there'll be 2 main switches, solar inverter and battery inverter. There must also be some disadvantages, and one of them is that it adds to the IES capacity. Now that's the Inverter Energy Systems capacity. That's kind of the sum of all the inverters behind the meter, behind the DNSP's meter. And there is limits on that provided by the DNSP. So for instance, if you have a limit of a maximum of 5 kilowatts of IES capacity on a single phase installation, that may be already taken up by the solar inverter's 5 kilowatt rating, and therefore adding a 5 kilowatt battery inverter may not be approved. Another disadvantage of this configuration, as I've drawn it, is that the solar will only work when the grid's present, because solar inverters, and including battery inverters, are required to comply with 4777 Part 2 and isolate from the grid when it's not present. So if the grid goes down, as I've drawn this installation, there is no solar, there is no battery. So it's purely a self-use system. Let's look at another configuration where we have some advantages now in terms of reliability. Now this system here is also an AC coupled system, and I should reiterate that AC coupling is a way of referring to how does the DC solar, how does it get into the DC battery storage? It gets there via the AC bus. So it's coupled through AC. So we've got a DC solar PV system, a DC battery system, but the energy exchange is done through the AC switchboard. Now in this configuration, what's different about it is that we now have the ability to operate the solar inverter even when the grid is down. So if we take the grid down here, we'll lose some circuits, and these would be what I call the grid-only loads. A system that is designed to maybe provide only essential circuits might have things like resistive element hot water on a grid-only circuit. But as soon as the grid fails, the battery inverter actually can provide a stable voltage reference that will allow the solar inverter to continue working, because a solar inverter has to synchronize with a stable voltage and frequency, and the battery inverter in this case will take over that role. So now even when the grid's down, we can send energy from our solar system into our battery, so we can recharge our battery system. The pros and cons of a system like this, well, for a start, the solar works without the grid. There's no energy meter required. Now you might think that's not a big deal, but sometimes it's difficult to get the communication cable from wherever the battery inverter system's installed to the point of connection, which is where the energy meter should be. So that's sort of a pro. Cons, you are passing through all of the energy from the grid to the load center. So the internal transfer contactor inside that battery inverter will have a limit. So some of them are like 30 amps, 50 amps, 63 amps. You've got to consider that as a limitation, though it is possible with some battery inverters to have an external contactor. And there is an off-grid mode, i.e. whenever the grid fails, you're basically an off-grid system, some way of controlling the solar inverter when the grid's not present. The reason for that is when the grid's present, you can always spill surplus solar energy to the grid or export limit it, but when the battery inverter is effectively the grid, it can only absorb so much energy, and once the battery's full, it needs to be able to curtail the production of the solar inverter. Now let's look at a DC coupled system. DC coupling actually is the oldest way of charging a battery, but in terms of grid connected systems, the most common configuration is what's known as a hybrid inverter. So a hybrid inverter has ports for PV, ports for battery, and ports for grid. Now this is a basic system which is designed primarily for self-use. The reason for that is if the grid fails, we still have the same problem. If the grid goes down, that means this connection must isolate, and therefore there's no power to the loads in the installation. And you could say this is a small benefit, the solar continues to charge the battery even when the grid's down. But it does need the grid to be able to export energy. And the reason for that is we've got a single connection. So we've only got a single connection here, a single phase connection to the load center, and it must comply with 4777 Part 2, which is the grid protection standard. So that port therefore is going to isolate when the grid's not present. So we'd call this a self-consumed system or self-consuming system. So the pros, it's simple. It's an all-in-one system, i.e. one inverter, which is also a battery charger, which is also a solar PV inverter. And it can charge that battery even when the grid's not present. The cons are it does require the energy meter for the same reason. It needs to know about the energy exchange with the grid. Are you actually consuming energy on your loads? And therefore, should it start to export battery and or solar to support the loads? And it only supplies loads when the grid is present. In this configuration, there is no backup. It comes as a shock sometimes that a battery system may not provide backup. It is quite common to have them configured as purely a self-use system. Now let's add backup to this. Now here we've got a switched backup circuit. It's often an external device such as an automatic transfer switch or ATS, and that allows a special function to occur. This ATS here will automatically disconnect the inverter's single AC port. So the single port here is going to be disconnected when the grid fails. So this port here will disconnect when the grid fails, and also will be isolated internally from the grid by the ATS, because it's controlled by the presence of the grid, what position that switch is in. But now the hybrid inverter can do a clever trick, basically convert the port from a grid paralleling 4777 compliant port to a standalone port, SA for short. And once it's in standalone mode, it now can actually provide power to a backup circuit like this. Now, it's a requirement that you identify that there is multiple sources. It's a multi-mode inverter, and there is multiple AC supplies in the switchboard, which means that when the main switch is off, some circuits may still be live. One of the characteristics of this kind of system is that there will be a break in supply. So let's say the lights will actually go off and then for a moment, but then come back on again when the hybrid inverter has reconfigured its AC port. So the big plus here is it does provide backup. Often it's of a limited capacity, so that needs to be considered. So that disconnection can be, 10, 30, 60 seconds, can be quite a while. The external contactor is another piece of equipment that's going to be installed, so that can add to cost of installation, and it is somewhat more complicated. However, there is another option, which is where that transfer is built in. Now here we've got a hybrid inverter with two AC ports. So we describe them as a grid port and a backup port. So this would be the grid port here. And so that's a 4777 port. And this is our backup port, sometimes called an EPS or emergency power system port. Now the EPS port can be live all the time, or it can be, depending on the software configuration of the hybrid inverter, only live when the grid fails. But it makes for a simpler installation. We don't have that external ATS. But effectively it's providing the same service, though there may be virtually no break, typically milliseconds of transfer time when the grid fails. Okay, so in terms of pros and cons, it's much simpler to install. But one thing to consider is that hybrid inverters with a backup function typically have quite a small backup capability. So for instance, it might be pitched as a 5 kilowatt hybrid inverter, but when you read the compliance label, it says backup circuit 2300 VA, or roughly 2.3 kilowatts. So in backup mode, not nearly as powerful. It is possible to have both AC and DC. I should point out this DC coupling, why it's called DC coupling. It's pretty obvious that the solar DC actually can go straight to the battery. So that's why it's called DC coupling. There's no path through an AC bus to be able to get that energy into that battery system. But you can have both. Here we've got a DC coupled system with what I call a virtual AC coupled system. So you can have both. Why would this be the case? It may be that the customer already has a grid connect system, so they already have the solar inverter and a PV array, and they want to add battery storage, but they also want to add more solar. And so a hybrid inverter is an easy way to add both at the same time. And the same issue is that the meter here needs to communicate with the hybrid inverter to tell it when to charge and when to discharge based on whether there's surplus solar from the existing solar inverter or whether the loads are drawing power from the grid. So pros and cons, it can charge the battery from both solar sources, from the existing solar inverter and from the direct connected PV array. It does, however, add to the total IES capacity, the inverter energy systems capacity of the installation, because there's now two inverters, and it will require that energy meter. It may, in this configuration, actually have no backup, but it's possible to have hybrid inverters with that multi-mode functionality where they've got both a grid port and a EPS or backup port. Now let's go off grid for a bit of a variation. This is what I call a solar or a diesel solar battery hybrid system. Now it's got a combination of a battery inverter and a solar inverter, very similar to what we looked at earlier, but instead of there being the grid on the left-hand side, we've now got a generating set. The big difference with this configuration is the battery inverter now has to understand it can't export energy out to the generating set, so it has to have a reverse power protection functionality, and unfortunately you can't turn surplus electricity back into diesel, so it has to protect that gen set. So there's some programming differences, but this is an AC coupled system. Remember, we've got DC here passing through to get to the battery, which is DC, passing through an AC network. And so it's a AC coupled off-grid system with a generator backup. So in terms of pros and cons of this system, the genset may be run at near constant load or even intermittently, because the battery inverter can choose to charge the batteries and supply the loads, and can adjust the amount of charge going to the batteries to continuously supply the loads as required, and any surplus can go to the battery. So that's better for generating set loading. And we've also got two independent sources of base load power. We've got a battery inverter system and we've got a generator. So there's some redundancy in case of failure of, say, the battery inverter system. The cons are, once again, that inverter is going to have a pass-through capacity limit on its internal contactor, how much it can pass through from the generating set to the load center. And it does require some coordination between generating sources. Typically, in an AC coupled off-grid system, it will either be frequency controlled or what they call managed, using communication protocols between the battery inverter and the solar inverter. Well, you can actually do it as a DC coupled system off-grid. So here we've got a DC coupled system. Why is it DC coupled? Because the solar energy which is DC, goes through a charge controller directly to the battery. Now, there's a big plus with a DC coupled off-grid system is it's a guaranteed way of charging that battery. You don't need the battery inverter to be turned on at all to charge the battery. Maximum power point trackers, MPPT for short, are very, very efficient. Typically 99% efficient, and very simple in terms of their electronics, and so highly reliable typically. So this is a DC coupled off-grid system. It also means we can size our PV array to our load energy requirements and size our battery inverter to our maximum demand. Because it might be a site where we only have a small maximum demand. Let's say we only have 2 kilowatts of load, but it's continuous. It's 24 hours a day. This might be a telco site, for instance, which means we're going to be needing about 48 kilowatt hours of energy every day. There's going to be some efficiency losses, but let's keep it super simple here. 48 kilowatt hours of energy a day coming out of that battery, and we've got to replace that with solar. So we've got to size our solar system to provide that 48 kilowatt hours of charge into that battery every day. So we can size them separately. That's a little bit of a plus when you're looking at a DC coupled system. Well, that brings us to the end of the system configurations for solar panels and batteries on-grid and off-grid.